Hi ladies and gentlemen, in this video we are going to talk about the rest of section 2.2. We will talk about the interpretation of probability in terms of the relative frequency, and we will show you how you can calculate the probability of an event. Here is your homework for this part. Also, you can have a look at examples 2.15 and 2.16 in section 2.2. From chapter 1, all of you know about frequency and relative frequency. In the frequency of x is the number of times that occurs in the data set. And the relative frequency of x is the number of times that x appears in data sets over the number of observations in data sets. So, for example, we have a group of people consisting of 500, and we have this frequency table for variable gender. Female, male, and consider that, or suppose that the frequency of females in this group is 200, for male is 300, so in total we have 500 observations. The relative frequency can obtain by dividing 200 to 500, and for male 300 over 500 is 0.4, 0.6, and in total 1. So the relative frequency here show that 40% of people are female and 60% of them are male. Now consider an experiment that can be repeatedly performed in an identical and independent fashion, such as rolling a dice or throwing a coin. Let A be an event consisting of a fixed set of outcomes of the experiment, such as heads in throwing a coin or 6 in rolling a dice. Now assume that NA is the number of times that event A occurs out of n repetition of the experiments. Look at this picture. In this picture, you can see that we have thrown a coin, for example, for 50 times, 100, 1000, and 10,000 times, and we have obtained the number of heads. Here 0 indicates heads and 1 indicates tail. You can see by using the formula of the relative frequency, we can obtain the probability of heads for this specific coin. As you know, the probability of head and tails for a fair coin are equal to 0.5. So please note that if you want to obtain an accurate result for probability of an event or an outcome, you have to increase the number of repetitions of the experiment. For example, look at here. Here you can see when the number of the repetitions are small, the relative frequency is not close to the expected values of 0.5, but by increasing the repetitions, you can see that the relative frequency tends to the expected value of 0.5. So the probability of event A can be interpreted as the limiting relative frequency of event A. In this example, in this example, for large number of tosses, this experiment shows that a head will appear on approximately half of tosses and tail on the other half. Okay, now how we can determine probabilities? Let EI denotes all the simple events in S. So we can write S as E1, E2, E3, and etc. Now we want to calculate the probability of compound event A. What we should do? Step 1. At first we should obtain the probability for each of EI. And then by adding together of the probability of EIs that are in the compound event A, we can obtain the probability of A. For example, for rolling dice, the sample space is 1, 2, 3, 4, 5, and 6. So E1 is 1, E2 is 2, E3 is 3, E4, E5, and E6. You can see that the simple events are disjoint. Look at here. The intersection of E1 and E5 is empty. The intersection of E2 and E6 is empty. The intersection of E3 and E4 is empty. So the simple events are disjoint. So from the axiom 3 for finite collection of disjoint event, we can say, for example, for A as 2, 4, 6, we can write the probability of A is the probability of E2 union E4 union E6. So from axiom 3, it's the probability of E2 because they are disjoint plus probability of E4 plus probability of E6. So by using the probability of simple events, we can obtain the probability of a compound event by adding the probability of simple events. Look at this example. Here S is 5, 6, 7. We have 3 simple events. E1 5, E2 6, and E3 7, and suppose the probability of each of them are 0.1, 0.4, and 0.5. Please note that the probability of these simple events are not equal in this example. Now what is the probability of event A occurring if observation is 6 or greater than 6? So S is 5, 6, 7. So A is 6 or greater than 6. It means 6 and 7. We have E1 as 5, E2 as 6, E3 as 7. So the probability of A is the probability of E2 union E3 is, because they are disjoint again, is the probability of E2 plus probability of E3, and the probability of E2 is 0.5, 0.4, 0.5, so 0.4, 0.5 is 0.9. What happens if the probabilities distribute and the probabilities the probability are distributed equally? At first, look at this example. Consider a coin that is fair. So it means the probability of head is equal to probability of T. And we know S for throwing a coin is H and T. So this one is E1 and this one is E2. When the probability of H or E1 is equal to probability of E2, we consider this probability as, for example, P, small p. Now we are going to obtain P. All of us know that P, probability of S from axiom 2 is 1. Now we can, because E1 and E2 are disjoint, we can write the probability of S as the probability of E1 union E2. So it's the probability of E1 plus probability of E2. So the probability of S from axiom 2 is 1, is the probability of E1 plus probability of E2. So we consider that as P plus P, a small p. So 1 is equal to 2p. So P is 1 over 2 or 0.5. So you can see that for a fair coin, the probability of head and the probability of tail are 0.5. But now consider that we have a coin that is not fair, and we know that the probability of heads is twice of the probability of tail. Okay, how we can obtain the probability of H and T? We want to obtain the probabilities of simple events. Again, S is HT, and we have two simple events. The probability of E1 and probability of E2. Okay, if we set the probability of the probability of E2 as P, according to this sentence, the probability of H is twice of the probability of T. It means the probability of H is 2P. Again, we know that from axiom 2 that the probability of S is 1 and E1 and E2 are disjoint. So the probability of S is the probability of E1 union E2 is the probability of E1 plus E2, the probability of E2. So 1 is equal, probability of E1 is 2 pi, the probability of E2 is pi, then 1 is 3 pi, P and P is 1 over 3. So the probability of T or E2 is 1 over 3 or 0.33, and the probability of E1 is 0.67 or 2 times 0.33. So, if in some experiments we assume that for a total of n outcomes, and equal probabilities, then we say that that experiments or that sample space is, has or the events in that space are equally likely outcomes. We have equally likely outcomes if we assign equal probabilities to all n simple events. Again, assume that the probability of all the simple events are equal for S consisting of E1, E2, E3. So the probability of each of them is 1 over n, and the summation of them are 1. Again, if we assume that the probability of all the simple events in a sample space are equal, then we say we have equally likely outcomes. The probability of each of them are 1 over n. N is the number of outcomes in S, and the summation of all probabilities is 1. For example, if we have a dice and we roll a dice, S is 1, 2, 3, 4, 5, and 6. If the dice is fair, it means the probability of 1 is equal to probability of 2 is equal to probability of 3, and so on. So the probability of 1, E1 is 1. The probability of 1 is 1 over 6. This one is E2. The probability of E2 is 1 over 6. E3, E4. So the probability of E3 is equal to probability of E4, probability of E5, the probability of E6, and so all of them have the same chance to happen. Now again we want to solve this example again, but suppose now these simple events are equally likely. How we are going to solve it? Again we have S as 5, 6, 7. So the probability of this one is 1 over the probability of this one, and the probability of this one is 1 over 3. So A is 6, 7. So the probability of A is the probability of 6 plus the probability of 7 is 2 over 3. So when the various outcomes of an experiment are equally likely, it means the same probability is assigned to each simple event. The task of computing probabilities reduces to counting. In particular, if ns is the number of outcomes in a sample space and na is the number of outcomes contained in an event A, then the probability of event A, or the relative frequency of event A, is ns over na over ns. It means the number of simple events in A and the number of simple events in S. So here the number of, for example, if we want to solve this from this new approach, so the number of simple events in S are 3 and the number of simple events in A are 2. So the probability of A is 2 over 3. Or for example, in rolling a dice, suppose these events now we want to obtain the probability of each of them. So the probability of A is 2 outcomes or 2 simple events over 1, 2, 3, 4, 5, 6 simple events in S. The number of outcomes in S, the number of outcomes in A, the probability of B, again the number of outcomes in B, the number of outcomes in S, the probability of C, the number of outcomes in C, the number of outcomes in S. All of us knows that the probability from proposition 1, the probability of a null event is 0. But here the number of simple events in D or outcomes in D, the number of outcomes in S. for S, the probability of S is the number of outcomes in S over the number of outcomes in sample space or S, the probability is 1. That it's the axiom 2.